Again, if you are ready, we can start.
Okay, good. Thank
Okay.
you.
Good morning, everybody. So welcome to this second class of Flavour and Effective Theory session lecture given by Jernej Kamenik from Slovenia, from Ljubljana. And without hesitation, I give the word to Jernej to start the class.
Okay, thank you. So I've tweaked my setup a little bit, so I hope it goes a bit more smoothly than yesterday. We'll see. Oh. Okay, so today I will spend, I think, the whole lecture on continuing where we left off yesterday in establishing the source of flavor in the standard model. And today we'll spend discussing how we test this in experiments using measurements. So this lecture will be devoted to testing the CKM. So to start off, let's establish a couple of properties of flavor conversion in the standard model. So as we saw yesterday, all of flavor conversion in the standard model, or flavor violating processes in the standard model, proceed or are parameterized by three CKM angles, so three parameters. Flavor conversion in the standard model is mediated by charge current electroweak interactions. So remember that the CKM matrix elements only, so after rotating to the mass basis, only entered the interactions of the couplings of the charged W bosons with the quarks. And finally, these charge current interactions only involve left-handed Karl fermionic fields. Okay, so let's see how we can conveniently test these properties. And in particular, today, most of the discussion will revolve around testing this parameterization in terms of three CKM angles. And also the second half probably of the lecture will be about also testing the unique source of superviolation, namely the phase of the CKM. So let's start by choosing a convenient parameterization of the CKM in order to test it. So let's discuss the parameterization of CKM. Now, by convention, the CKM is usually written out in so-called mass ordering convention, where the rows and the columns of the CKM are ordered by the increasing masses of the corresponding flavored quarks. And so in this mass ordering, the CKM is conventionally written as the following. So just to establish the notation of the CKM matrix elements, so we have VUD, VUS, VUB in the first row, then we have VCD, VCS, VCB in the second row, and finally we have VTD, VTS, VTB in the third row. Okay. Now, what is important in choosing a convenient parameterization which would reflect the 4 physical parameters of the CKM is that there is a clear structure in the sizes of the elements of the CKM. In particular, there is a strong hierarchical pattern in off-diagonal elements. In particular, the diagonal ones, so the moduli of the diagonal CKM elements, so VUD, VCS, and VTB are all of the order 1. On the other hand, the first off-diagonal elements, VUS and VCD modulus, are approximately the same size and are smaller than 1. If we go further off the diagonal, so in the second, so the third and the second off diagonal matrix elements are even smaller. So VCB and VTS are approximately of the same size of 4 times 10 to the minus 2. And finally, the most off-diagonal elements, VTD and VUB, are even smaller, or an order of magnitude smaller, and amount to approximately 5 times 10 to the minus 3. So a useful parameterization can actually make this hierarchical structure of the CKM explicit. And one such parameterization, which is mostly used in the literature, is the so-called Wolfenstein expansion. And the expansion is actually an expansion in a single parameter, denoted by lambda conventionally, which is defined as the modulus of the VUS matrix element. So the expansion parameter here is roughly 0.22. Now one can, using this parameter, expansion parameter, one can do a systematic expansion. And so to make it even more exact, one can, let me just share one slide with you. Okay, so here I've written out the CKM in a particular parameterization, which is not the Wolfenstein parameterization, which is the so-called PDG parameterization, which is manifestly written in terms of 3 CKM angles, namely the C's and the S's are the cosines and the sines of the corresponding angles, and a single phase, which is here denoted with delta. Now, of course, this is not a unique parameterization, because especially you can see that the way we introduce the phase is, of course, to some degree arbitrary. Now, when we can then go from this general PDG parameterization, which does not necessarily reflect any hierarchies in the CKM, it could as well parameterize any kind of unitary matrix with a single phase. The so-called Wolfenstein expansional parameterization then uses the fact that sine of the 1,2 angle is small, and this is what it defines as lambda, and this is our expansion parameter. And then the other off-diagonal elements, namely the sine of the 2,3 angle and the sine of the 1,3 angle, are then written out in terms of higher powers of lambda. And in a general way, so for example, the sine of the 2, 3 angle is lambda squared times a order 1 parameter A, while sine of the 1, 3 angle is order lambda cube and is parameterized in terms of additional 2 order 1 parameter, a real rho parameter and an imaginary eta parameter, which parameterizes the presence of a phase in the off-diagonal, so the mostly off-diagonal elements of the CKM in this particular parameterization. So let's see. Yes, so one can do this using these definitions of the or reparameterization of the 3 angles and a phase. One can then exploit the smallness of lambda to do a systematic expansion in lambda. And for example, in this case, I've written out the expansion up to order lambda cube, which is the leading order at which all the CKM elements are non-vanishing. And what is useful and important about this Wolfenstein expansion is that at any given order of the expansion, the resulting matrix preserves unitarity up to that given order. So here, as we've expanded up to order lambda cube, the matrix that we've obtained is manifestly unitary up to order lambda cube. The present precision in experiments actually requires us to go to higher order in this expansion in lambda. And what is usually employed nowadays in comparing or interpreting measurements of the CKM elements is the expansion up to order lambda to the 8th, I think, lambda to the 7th, sorry. So including all the terms up to order lambda to the 5th, and then the next correction comes in, I think, order lambda to the 7th. And furthermore, so this is how this expansion looks to this order in the expansion. And for later convenience, I've also defined 2 parameters which are actually used in visual representations of the constraints on the CKM matrix elements, which are related to rho and eta, and they include order lambda squared corrections. So they are conventionally they are denoted as rho bar and eta bar, and you will see these parameters pop up later when we discuss the actual constraints from individual measurements on the CKM. Okay, so let me now let's see. Yeah, let me now switch back to the other. Okay, so as we said, what an important property of the CKM is its unitarity, and that it's the testing of CKM unitarity is an important probe of the standard model description of flavor. So let's discuss the unitarity of the CKM a bit more in detail. Now, one can write out a complete set of unitarity constraints on the rows and the columns of the CKM, which will be sum over k, VIK, complex conjugate, VJK equals delta ij for any ij going from 1 to 3. And similarly, so this is summation over columns, and then we have summation over rows. Sum over k, VKI star VKJ equals delta ij. Okay, this is nothing else but writing out the unitarity constraint or the unitarity condition of the CKM element by element of the unit matrix, which results as the unitarity constraint. So while in principle one could test all of these different unitarity conditions, it turns out that phenomenologically it is most interesting to fix, so for the case where I equals 1 and j equals 3. So let's consider the case where, as an example, which turns out to be the most useful one, for I equals 1 and j equals 3. So if we write out the unitarity condition for this case, we obtain that V UD times VUB star plus VCD VCB star plus VTD VTB star equals 0. So why is this particular choice of I equals 1 and j equals 3 interesting? It's because in this particular sum, all three terms, if written out in terms of the Wolfenstein expansion, turn out to be of the same order in lambda. So we have three quantities which are of the same order. So all of three contribute with the same power of probing the relevant flavor parameters. This is not the case, of course, for other related constraints. So choosing different I and j, because of the hierarchical structure of the CKM, typically most of these constraints will be dominated by a single term. So whenever we have a diagonal term present, that will completely dominate the whole sum. And only when we go completely off diagonal, we can arrange these terms such that all three of the same are of the same order. And in particular, one can make this manifest in the CKM parameterization, namely if we arrange slightly these three terms, namely we divide by the middle term, we can write this same unitarity condition as VUD VUB star over VCD VCB star plus VTD VTB star over VCD VCB star plus 1 equals 0. And now we can write all the CKM elements which enter in terms of the Wolfenstein parameters, and it turns out the above equation reduces to the following simple equation, which is rho bar plus I eta bar plus 1 minus rho bar minus I eta bar minus 1 equals 0. And this condition is now, I've used the expansion in the Wolfenstein parameters up to order lambda quartic. So this relation is exact up to order lambda to the fifth. And we see that since all the parameters which enter this equation are order 1 in principle, so there are no powers of lambda involved, that they will tend to be all of the same size. Now, what we've arrived at is we have two real parameters, which satisfy a linear equation. And such an equation is nothing else but the equation of a triangle in a plane. So we can visualize this condition, this unitarity condition, in a plane of the two parameters, in this case, rho bar and eta bar. And then So one of the sides of the triangle can be taken just as 1 because the third term is just 1. So we can take 1. And then this condition will define a triangle which has an apex somewhere in the plane. And the angles and the sides of this triangle turn out to be invariant under any phase transformations of the quark fields. So any reparametrization of the quarks, and so they are observable quantities. And so let me define, for future reference, let me also define the notation of the angles. So we typically denote the first angle here as gamma, the upper one is alpha, and this one is beta. Okay, so using measurements of rates and CP asymmetries, as we will discuss in a minute, we can, in principle, measure both the sides and the angles of this triangle. Okay, and in general, thinking about the whole structure of the CKM and the parameters of the CKM, what we are actually doing here when we are determining this particular triangle, which we derive from one of the unitarity conditions of the CKM, is basically projecting all the measurements which are sensitive to the flavor dynamics in the standard model onto this particular plane of parameters. So in general, since the CKM is parameterized by 4 parameters, the parametric space of the standard model flavor has 4 dimensions. And in this case, we've chosen a particular projection plane in this 4-dimensional parameter space to project all the measurements onto, and we can project all the measurements which are sensitive to the standard model CKM parameters onto this plane. And let's see how this plays out in practice. So let me switch back to the slides. Okay, so since we've projected the measurements onto a plane which only contains rho bar and eta bar, we need to, in order to actually do it, we need to fix the other 2 parameters, which is the expansion parameter lambda and also the A parameter. And so one can do that using semi-leptonic meson decays. For example, lambda, or the modulus of VUS, can be extracted from the comparison of the standard model predictions and the measurements of the semi-leptonic K2 pi L nu decay widths or rates or branching fractions. And similarly, the modulus of VCB, which is given by lambda squared A. So one can then use this measure, one can extract A from a measurement of the corresponding semi-leptonic rates of B mesons. In particular, the most precise extraction of A is currently possible from measurements of inclusive semi-leptonic B decays to charm final states. So then once we fix lambda and A, then we can project other measurements of, for example, of flavor changing charge current mediated processes onto the plane of rho bar eta bar. And first such measurement, which is important, such constraint, which is important, which measures one side of the CKM triangle, which is given by a rho bar, so rho bar square plus eta bar square, is the measurement of the modulus of the VUB CKM matrix element, which is possible from the measurements of the rates, Senatonic inclusive BDK rates to charmless final states. So this is if the measurement of VCB or A is made by B to C charge currents, then the measurement of VUB or rho bar squared plus eta bar squared is made by B to U charge currents in the Stern model. Okay, and this measurement then can be projected on this plane and is basically, if it was exact, would give a circle, but since there is an uncertainty given by both important theoretical uncertainties and experimental uncertainties, which we will discuss later. So what are the main, especially theoretical uncertainties, which enter Flavour measurements? This then furnishes a band, a circular band in this rho bar eta bar plane. Then one can also use measurements of time-dependent and time-independent CP asymmetries, which we will discuss in some length in a few minutes, to measure the angles of the CKM triangle, and in particular, a measurement of time-dependent CP asymmetry in B decays, neutral B decays to J psi K short final states, measures the beta angle in this CKM triangle, and the beta angle is related, again, can be written out explicitly in terms of eta bar and rho bar, and the expression that one derives is this one that is written out, and the measurement of this time-dependent CP symmetry then projects onto this plane, and since there is a sign ambiguity involved, one gets a twofold solution for this angle. Similarly, one can use now measurements of rates of B to DK final states to extract the other CKM angle gamma, which again can be written out in terms of rho bar and eta bar, and the current measurements allow to now superimpose this or to constrain this angle to lie in this purple cone. And we already see that with these three sets of measurements, we can already over-constrain this the CKM, in a sense that there is no guarantee that these three sets of measurements would overlap in a single region in this plane. And as you see, they do. Of course, there are other measurements which one can superimpose. So for example, there are related measurements using of rates of BDK rates to pi pi rho pi and rho rho final states, which measure which are sensitive to the third angle of the CKM triangle, namely alpha. And I don't write the expression in terms of the rho bar and eta bar because it's somewhat lengthy and cumbersome. And so there are also measurements which are sensitive to the other sides of the triangles. For example, the ratio of neutral B sub D and B sub S oscillation frequencies is proportional to the ratio of VTD or VTS modulus squared, which can be again written out in terms of rho bar and eta bar, and the measurements of these ratios and comparison with the Stern model predictions can then be again superimposed and furnish this orange band in this plane. And finally, one can also use information coming from kaon decays. So if you remember, yesterday we discussed that superviolation was first discovered in the kaon system, observing some superviolating k to pi pi decays. And in fact, these decays still impose an important constraint on the CKM parameters, which in this plot now is visualized in the pale pink band. Again, the written out in terms of rho bar eta bar, the expression is somewhat lengthy, so I don't write it out explicitly, but nevertheless, it's an important constraint. And putting it all together, the first observation is that all the constraints, all the different constraints which come from different sectors of the theory, which involve both CP asymmetries, rate measurements of neutral measurements, rate measurements of charge measurements, which don't oscillate at all, oscillation frequency measurements, and also involve both B and kaon decays. They all converge to the same region in this rho bar eta bar plane, which signals the consistency of the CKM description of flavor as projected on this plane of rho bar eta bar. And one can then use the combination of this measurement to finally determine a global average of the remaining two parameters of the CKM, namely the rho bar and eta bar, which are currently determined to a precision which is between maybe around 10% already, or even better than 10%. Okay, yes. So most of these measurements.
Yeah, Nate, sorry, before going on, there's a question. Intuitively, how could we come up with the Wolfenstein parametrization?
Sorry, can you repeat the question, please?
Sure. How could we come up with the Wolfenstein parametrization intuitively?
Oh, so the Wolfenstein parameterization is very simple in the sense that if you just write out the moduli, so the moduli of the CKM, at least some of them, are directly measured. No, for example, in kaon and BD case, one can already establish that the moduli of the off-diagonal elements, namely VUS, VUB, and VCB, are small and they exhibit a clear hierarchy, right? So then one can, if choosing any particular parameterization which is general, like the PDG parameterization, one can then see that the angles, the off-diagonal angles, have a hierarchical structure. And it turns out that due to the numerical values, so basically that VCB is almost squared of VUS, and that VUB is almost cube of VUS, then one can think about parameterizing these signs of these angles in terms of expansion in a parameter. And immediately after you do that, then you end up very generally with this kind of parameterization. Okay, so it's a combination of observing the measured values of some of the elements which are precisely measured, and then accommodating the observed hierarchy with an appropriate expansion. And once one defines the lambda A, rho, and eta like it's done here, then it's completely general, and one can do this expansion in any given order in lambda.
Okay, thanks a lot.
Okay. Right. So this is all the constraints. Yes. So the establishing of this CKM paradigm of flavor in the standard model is basically one of the main legacies of the so-called B factories, which were operating in the early 2000s, and they helped establish this picture. So to really understand the progress of our understanding of flavor, which was due to these measurements done by B factories, because as you will notice, most of these measurements which enter this constraints in the rho bar eta bar plane are actually measurements done with B mesons, except the last one, the first, so the measurement of lambda from k on decays, and the constraint coming from superviolation in k on decays, namely epsilon k. All the other ones are basically done using B decays or B oscillations. And this was the main purpose of the B factories, to produce large amounts of B mesons so we could study their decays and oscillations, and CP symmetry is related to these oscillations and decays. And to appreciate the progress, so before I put here a time series of these constraints in the rho bar eta bar plane. So the first one is a history plot from 1995. So this is before the B factories. And the uncertainty on the rho bar eta bar plane, even though the consistency of the measurements which were at that time available seemed to be established, there was a fairly large uncertainty in this determination of the rho bar and eta bar. And soon after the B factories reported their first results, this determination of the CKM was very much improved, as is shown in this picture from 2004, which was after a few years of running of the B factories. And nowadays, so with the full data set of the B factories, and including the recent LHCb measurements, especially of the gamma CKM angle, we see that the already at present the determination of rho bar eta bar is very, very precise, and the measurements exhibit a good consistency, which is really important. So we don't see any sizable deviations in the measurements of flavor from the description given by the standard model, at least not in this particular when testing for unitarity of the CKM. Okay, so let me switch back to handwritten notes. Okay, so what the B factories helped establish is that very likely superviolation in flavor changing processes is dominated by the CKM phase, and that the so-called Kobayashi-Maskawa mechanism superviolation, namely that superviolation in the standard model is driven by flavor conversion between the three generations of quarks, is at work in the measurements that we have been performed. Another important property of the CKM in relation to superviolation is that if we actually look at the values of rho bar and eta bar, so let me just for this purpose write them out again. So rho bar, remember, which is the real part of the 1,3 CK matrix element, once we factor out the lambda cube prefactor, is roughly 0.2, while the eta bar, which is the imaginary part of this element, is actually 0.350. And so in this particular polarization, we see that the phase in the CKM is not small. Phase is actually order 1 in the CKM. So the suppression of superviolation in the standard model does not come from a small phase, but it comes actually from the hierarchical structure of the CKM moduli. Namely, superviolating observables are suppressed by the smallness of flavor changing currents, not by the smallness of the superviolating phase itself. So you could claim that superviolation in standard model is order 1. However, observation of this superviolation is suppressed by the smallness of the rates where you can observe it, when you can observe it. One can also phrase this discussion closer to what we had yesterday. So in terms of the representation invariant quantity, namely the Yarlskog invariant. So we can consider a representation invariant measure of superviolation in the standard model. And this would be, so if we just take the representation invariant combination of CKM elements, which would be the imaginary part of Vij, Vkj, Vkl, Vil, where we sum over all the repeated indices. So one can check that this combination of CKM elements, when we sum over all the indices, is representation invariant and can be written out in general as a number, which I'll call JKM, times, in general, a sum over epsilon IKM epsilon JLN. Okay, so when we, so when we sum over M and N, okay? So we can choose any, so choosing any combination of I, J, K, and L, we obtain the same quantity because this is a representation invariant quantity, provided, of course, that I, J, K, and L are such that the sum on the right-hand side does not vanish. So these imaginary parts either vanish or they give a fixed number. And one can even derive the value of this representation invariant measure of superviolation in the CK matrix, and it turns out it's given in terms of the Wolfenstein parameterization, it's given by lambda to the 6 a squared eta. So what we observe is that, as expected, since it's a measure of superviolation, it's proportional to eta, which is the only imaginary parameter in the Wolfenstein parameterization. And also, it reflects the fact that the observables related to superviolation are suppressed, and they are suppressed because the measure of superviolation is suppressed by the smallness of the off-diagonal matrix elements. So it's suppressed by small mixing and to a large power, to the 6th power in lambda. So this measure in the standard model, plugging in the numbers, will give you 10 to the minus 5. Okay? So this is not yet the Yarlskog invariant of the standard model. Namely, to get to the Yarlskog invariant J, so remember, this was the imaginary part of the determinant of the commutator of the YU dagger and YD dagger, so the up and the down Yukawa matrix squareds. The whole Yarlskog invariant is then proportional to this JKM times a product over I and J, where we sum over only when I is greater than J, over differences of mass squares over V squared. So if you write out the masses in terms of the Yukawa eigenvalues, you'll see that this actually reflects the fact that you're dealing with a determinant of a commutator being the product of these mass difference squares. And plugging in the numbers, one obtains that the Yarlskog invariant in the standard model is of the order 10 to the minus 22. Okay, so CP-violation in the starter model is actually, even though it's tiny, so this Yarskog measure of CP-violation is very small, s10 to the minus 22. It's actually not small because the CP-violating phase in the CKM would be small, but it's small because it's suppressed by small angles and by the hierarchical small masses of the first two generation quarks. Okay, compared to the natural scale of the electroweak theory, which is the electroweak VEV. Okay, so this sums up the general discussion of testing the CKM. Now let's dive into the details a bit and try to understand how we actually derive constraints on rho bar and eta bar by and especially eta bar. So we're especially interested in the determination of this phase of the CKM using this CP asymmetries related to neutral meson oscillations. So this we will devote the next 45 minutes, will be a closer look at CP violation in neutral meson mixing. And for simplicity, I will focus on a particular neutral meson system, namely the system of B sub D mesons. In particular, I will denote B naught as the neutral B meson state with the Flavour composition B bar D, and I will denote B naught bar as the B naught B meson system with the Flavour composition B D bar. Now these states are not mass eigenstates, but they have definite CP properties, namely performing a CP conjugation, so charge and parity conjugation, on a B naught state will transform it into a B naught bar state up to a phase, which we denote as psi B. And similarly, performing CP conjugation on B naught bar will yield a B naught state, again up to a phase, which is now just the minus of the previous one. Okay, because of course we want CP conjugation squared to reproduce to be the identity. Okay, so next we can observe or parameterize the time evolution of a given state, which is a linear combination of the B naught and B naught bar states. So let's consider the time evolution.
Yeah, Nate, sorry, before
Yes.
going on, why cannot we say that the mass in these states, they do not have definite CP? Is a question.
Yes, so we will see this in a minute when we write out the form of the total Hamiltonian. So of course, the mass eigenstates are the eigenstates of the total Hamiltonian. And since the total Hamiltonian of the standard model does not conserve CP, the CP eigenstates are not mass eigenstates. This is a short answer. A more technical answer will be hopefully more clear once we write out this explicitly.
Okay, thank you.
So let's consider the time evolution of a state. So let's prepare a state at time 0, which we denote as psi 0, which will be in general a linear combination of a B naught state and a B naught bar state, okay? And the coefficients in the proportionality factors of these two contributions, or these two states, will be denoted by A and B, and the naught in the parentheses denotes that this is at time 0. Now, at any given time t, this state will evolve, and the evolution is given by the evolution of the coefficients. So we have A of t times the B naught plus B of t times B naught bar. But we need to take into account that the neutral B mesons are not stable particles, they decay. So after time, these states can evolve in other states which are not B naught and B naught bar, but involve the decay products of B naught and B naught bar. So we have to add terms, let's denote them by Ci, so C1 of t times some decay final state F1 plus C2 of t times F2 plus so forth, okay? So this is now a completely general discussion of the time evolution of state, which at time 0 was composed only of B naught and B naught bar, but after some time, we can still have a combination of B naught and B naught bar, but we can also have, some of the B's have decayed, so we can also have a combination of other final states. They are decay final states. Okay, so this is B naught bar decay products. So when we discuss B oscillations, we are only interested in the first two terms. Okay, so we will truncate this time evolution to just the time evolution of A and B. Okay, so we will only be interested in the determination of A of t and B of t. Now, to do that, let's consider the Hamiltonian, which governs the time evolution of B naught and B naught bar. And in general, we can write the Hamiltonian, since it describes the time evolution of states which decay, it will contain a Hermitian and an anti-Hermitian contribution. So the Hermitian contribution, let's call it M, is the so-called dispersive contribution. And in addition, we have an anti-Hermitian contribution. Let's write it manifestly as in terms of a Hermitian operator or matrix, gamma, such that it's manifestly anti-Hermitian. And this other contribution is typically called absorptive. Okay, so the names dispersive and absorptive come from the fact that the to M, so to the dispersive part, only off-shell intermediate states will contribute, and they will describe oscillations of B mesons. On the other hand, the absorptive part gets contributions from on-shell intermediate states, and they actually describe the decay of B naught and B naught bar into other final states. Now, in this parameterization of the Hamiltonian describing the time evolution of the B naught and B naught system, M and gamma are now time-independent Hermitian 2x2 matrices. So M and gamma are time-independent Hermitian 2x2 matrices. And they parameterize the time evolution of the B naught and B naught system in full generality. So in terms of this effective Hamiltonian, now I can write the time evolution of the coefficients A of t and B of t in terms of a two-column vector. as given by H acting on A of t, B of t. And we'll be interested in the eigenvectors of this Hamiltonian. So one can write the eigenvectors. And let's denote the eigenstates of this Hamiltonian, which we will order by mass. So we will denote them as B, L, and H as light and heavy. These are the eigenvectors. And they will in general be a linear combination of B naught and B naught bar. So we can write out the coefficients of this linear combination as PLH times B naught plus minus QLH B naught bar. And by unitarity, we know that PLH squared plus QLH squared equals 1. Okay. However, we know more. We know that if the theory is described by a local quantum field theory, it needs to satisfy CPT, and if CPT holds, then we can further show that these matrices M and gamma satisfy further constraints, namely the diagonal elements need to be the same, M11 equals M22, and also gamma 11 equals gamma 22. And from these conditions on the Hamiltonian, one can derive that PL actually needs to equal PH. So in the following, we'll just denote them P. So we will assume CPT, and we will denote it commonly by P. And similarly, QL has to equal QH, and we will denote it simply by Q. So next, let's consider what would be the condition of CP conservation. So on this system, so if CP was conserved, then one can show that the argument of M12 has to equal the argument of gamma 12. Okay, so notice that the CP conservation does not impose that the phases of M12 and gamma 12 are 0. It just imposes they are equal. Okay, this is the representation invariant statement, that these phases are equal. They might not be 0. And so from this constraint of CP conservation, one can derive then that in the limit of CP conservation, the modulus of Q over P needs to be 1. Okay, so one way of testing the presence of CP violation is to test whether Q over P deviates from 1. This is one simple test of CP violation. Okay, so to proceed further, let's define some further properties of our neutral B-meson eigenstates. So let's furthermore define the M will be the average mass of the two eigenstates. So small m will be m light plus m heavy over 2. And similarly, we will denote with just gamma will be the average decay width, gamma light plus gamma heavy over 2. And then we can also form the orthogonal combinations, namely we will define as delta m will be the difference between the heavy mass eigenstate and the light one, and the delta gamma will be, by convention, will be the difference between the decay width of the heavy eigenstate and the decay width of the light eigenstate. Now, in the literature, you will also often find the definition of related quantities, for example, x and y. And for reference, for example, what you often find as x is given by delta m over gamma, and what is given by y is typically defined as delta gamma over 2 gamma, okay? And notice the importance that delta gamma is, the sign of delta gamma is very much convention dependent, and one needs to be careful when comparing different papers, for example, which might use different conventions in the sign of delta gamma. So with these parameters defined, now we can actually solve exactly for the time evolution of our initial linear combination of B naught and B naught bar. So let's return to the time evolution and restrict our discussion to two cases where the initial state is prepared to be a pure CP eigenstate or Flavour eigenstate. So let's consider the time evolution of B naught of t, which will be defined by a state which evolves from a pure B naught at t equals 0. So basically taking in the above time evolution, this is basically taking B of naught equals 0, okay? And A of naught equal 1. And similarly, we will define the time evolution of B naught bar as the evolution of a state which is a pure B naught bar state at t equals 0. Okay? Now, in general, solving the above time evolution equations, one can derive the following time evolution equations, dependence. So B naught of t is then given by G plus of t times B naught minus Q over P times G minus of t times B naught bar. And similarly, B naught bar of t is given by G plus of t B naught bar minus Q over P G minus of t times B naught, where these time functions G plus minus of t are given by 1/2 e to the minus I m h t minus 1/2 gamma h t plus minus e to the I minus I m l t minus 1/2 gamma l t. Okay, this is the general solution for the time evolution of pure Flavour eigenstates. So typically, how we observe the time evolution of the mesons is that we observe their decays to some final state f after some time t. So let's consider the decay to final state f after time t. So we can parameterize the corresponding decay amplitudes as the decay of the B naught state to f via the action of the Hamiltonian, and we will simply define this decay amplitude as AF, And then we can, in the same way, we can parameterize all the CP-related decay amplitudes, namely the decay amplitude to the same final state F of the B naught bar state, we will denote as A bar of F, and then the decay amplitude to the F bar, so the CP conjugated final state of the B naught initial state, will be denoted by AF bar, and finally the decay to F bar of B naught bar will be parameterized as the A bar, F bar amplitude. Now, in general, all of these amplitudes can be different. Some can vanish depending on the final state, and some can be related. But let's leave the whole thing free for the moment and see how we can define measurable quantities in using these amplitudes. In particular, one can define a so-called time-dependent decay rate, which we'll define as the differential decay rate over time for a B naught at 0 time. So this is a decay rate where we produce a B naught Flavour eigenstate B meson at time 0, and then we observe its decay to a final state F after time t. Okay, so during this time evolution from time 0 to time t, the B naught can oscillate to B naught bar and decay, or it can decay directly, okay, to F. So again, using the above solutions for the time evolution and the parameterization of the decay amplitudes, one can write in complete general this time evolution or time-dependent decay rate in the following way. There is an overall normalization which we will not be concerned with. So let's just put the overall flux normalization as some constant and 0. Then the dominant time dependence will of course be an exponential decay dependence. And we also factor out the dominant decay amplitude, AF squared. We could choose any of the decay amplitudes, and we'll see, but let's just choose the one which will dominate if B mesons did not oscillate. Okay. Now this is, and then we can parameterize the actual interesting time dependence as 1 plus lambda f modulus squared over 2 times cosine hyperbolicus delta gamma t over 2 plus 1 minus lambda f modulus squared over 2 times cosine delta m t plus the real part of lambda f sine hyperbolicus delta gamma t over 2 minus the imaginary part of lambda f sine of delta m t. Just to be clear, the arguments of the trigonometric and hyperbolic functions. Okay. Okay. And similarly, one can write the so before continuing, let me define the parameter lambda f, which I've introduced, which is just the following combination, is just q over p times a bar f over af. Okay. And similarly, one can also write out the time-dependent decay rate of a B naught bar initial state B meson to f of t. And again, this one will be given by the overall normalization times e to the minus gamma t times A bar F modulus squared times, and now again, we have very similar expression as before, 1 plus modulus lambda bar F squared over 2 times cosine hyperbolicus delta gamma t over 2 plus 1 minus lambda bar F modulus squared over 2 times cosine delta m t, and then plus the real part of lambda bar F times sine hyperbolicus delta gamma t over 2 minus the imaginary part of lambda bar F sine delta m t. Okay, so it's very symmetric with respect to B naught and B naught bar. And I've now introduced lambda bar F as being P over Q times AF over A bar F. And so you notice by comparing this lambda F and lambda bar F, that lambda bar F is related to lambda F being just 1 over lambda F. Okay? And analogously, one can also define the time-dependent decay rates for decays to F bar, for example. So analogously for F bar decay rates. Now we can discuss the physics contained in this time dependent decay rates, namely what is the physical meaning of the different. So we have 4 different terms which have different time dependencies, and in particular the terms which are proportional to AF in the first case and A bar F in the second case. So the terms which remain when we put lambda F or lambda bar F to 0, those terms are parameterized decay without net oscillations. Okay, so for example, starting from a B, it oscillates, but it decays when it's in the B state, not the B bar state. Okay, so there is no net oscillation. On the other hand, the terms proportional to lambda F in the case of B naught and lambda bar F in the case of B naught bar parameterize the time evolution of decays which follow a net oscillation. So this is a B naught which oscillates and then decays as a B naught bar, or a B naught which oscillates and then decays as a B. So at the time of the decay, it's a B and not a B bar. And finally, the terms which are proportional to sine delta m and sine hyperbolicus delta gamma t over 2, those actually parameterize the interference between those 2 decay amplitudes. Okay. And finally, we also see that CP violation in this interference is possible only if the imaginary part of lambda f or lambda bar f is different from 0. Okay. Now there is a simple observable which one can define in terms of these time-dependent decay rates, which measures CP violation in these time-dependent decay rates, and is the simplest in case we define we are interested in decays when B naught bar decay to a CP eigenstate. So FCP. So this is a meaning that F equals F bar, right? Because it's a CP eigenstate, so F equals F bar. And in this case, so when F equals F bar, the above time evolution equation, so for the time-dependent decay rate, simplify furthermore, and one can define the following time-dependent CP asymmetry for decays of B and B naught bar to a CP eigenstate, if CP of T, which is defined as the difference of the time-dependent decay rates of B naught bar of 0 to F CP of T minus the corresponding time-dependent rate of B naught of 0 decaying to FCP at T over their sum. Okay. So one can define these asymmetries now for, in fact, while we've derived them for the B naught system, one can define them for any neutral meson system. In particular, also for B, for B sub S, for D naught, and also for the chaos, if you want. But they are especially interesting in the B and B sub S system because in B sub D, B sub S, phenomenologically, so experimentally, delta gamma, so the width difference of the two mass eigenstates, is much smaller than the mass difference, which is not the case neither for the neutral kaon and neutral D system, but it's true for the B systems. And this means that Q over P is approximately 1. Okay? Of course, it's not exactly 1, because if it was exactly 1, then there would be CP would be conserved. But because of this hierarchy of the parameters, one can define this CP asymmetry, the time-dependent CP asymmetry, in terms of we can neglect all terms, especially for the B sub D system, we can neglect all terms proportional to delta gamma and parameterize this CP asymmetry in terms of only two parameters, SF times sine delta MT minus CF times cosine delta MT, where now CF is defined as 2 times the imaginary part lambda F over 1 plus lambda F modulus squared, and CF is defined as 1 minus lambda F modulus squared over 1 plus lambda F modulus squared. Okay, so before we can use this time-dependent CP asymmetry to actually extract parameters of the CKM, we need to discuss phases in decay amplitudes. And namely, so since I'm running a bit short on time, maybe it's better if I switch to slides for this discussion. So, okay. Okay, so let's see. Where are we? Yes, so, okay, we've just derived these expressions for the B sub D system. And now, when we discuss the decay amplitudes of B to F transitions, there, of course, B to F and B bar to F bar are related by CP conjugation. And note that, or remember that complex parameters in the Lagrangian density appear complex conjugated after CP. So they have opposite signs after CP conjugation. And these CP odd phases are often also not denoted as weak phases. Okay, so there is a certain nomenclature which is used and to distinguish between different phases which can enter decay amplitudes. And those which are CP odd in nature, so they come from complex parameters in the Lagrangian or the Hamiltonian, they are so-called weak phases. but there are other kinds of phases which can enter your decay amplitudes, and those come from on-shell intermediate states, and they appear even because of the presence of cuts and poles in the scattering matrix, and they appear in the decay amplitudes even for real Lagrangian densities. Okay, so they, in particular, what is important is they have the same sign for both CP conjugate decay patterns, and in the literature they are usually denoted as strong phases. Historically, because they typically result from the strong interactions, stronger scattering of final states in hadronic decays. But what is important for us is they are CP even. They have nothing to do with CP violation. Now, in general, if we consider the decay amplitudes of a B meson decaying to an F final state, or a B bar meson decaying to an F bar final state, one can, in general, there will be one can parameterize it as a sum of different contributions to these decay amplitudes, which can have different weak and strong phases. Okay, so we can parameterize in terms of the moduli of the amplitudes with different phases, and each contribution can have a different strong phase and a different weak phase. So strong phases will be denoted by deltas, and weak phases by phi's. And then in the case of the measuring CP asymmetries or CP violation in neutral B meson decays to CP eigenstates, for example, one CP eigenstate which is being used to measure the angle beta in the CKM triangle is the eigenstate, the final state of J psi k short, which is a CP eigenstate. And then in this case, one can parameterize the AF and A bar F in terms of a single, so these decays are dominated by a single decay amplitude. They are tree-level dominated decays in the stellar model. And the CP conjugate decays, because they decay to a CP eigenstate, they carry the same strong phase, but an opposite weak phase. Okay, and because the final state, the CP eigenstate, there might be a phase associated with its CP conjugation properties, which is here denoted by eta f. So it can be either +1 or -1, depending on whether this state is a CP even or CP odd. Okay, so parameterizing the decay amplitudes in this way, which is again still very general, when the decay amplitude is dominated by a single weak phase amplitude, then one can write the corresponding lambda f parameter in terms of these phases. And what you see is that they only depend, lambda f now only depends on the weak phase. So the strong phase cancels in this ratio. And using the fact that in the B sub D system now, as I said, gamma 1,2 is much smaller than M12, which is related to the fact that delta gamma is much smaller than delta M. One can expand Q over P, and one observes that Q over P squared in particular is given completely in terms of this phase parameter between the B naught and B naught bar state, which we defined in the beginning. So one can then write lambda f in terms of the difference between the relative phase between the B naught and B naught bar and the relative weak phase of the decay amplitude, and is weighted by the CP parity of the final state. And then we can plug this into the S parameter governing the time-dependent CP asymmetry, so defined here. And we observe that this time-dependent CP asymmetry will then be proportional to this particular sign of the phase difference between psi b and 2 phi f. Okay. Now, we can actually determine these phases in the standard model, and they are completely given by the phases of the CKM elements. Namely, psi b is nothing else but the argument of M12, and the argument, so the phase of M12 is completely given by the BB bar oscillation amplitude, which is being mediated by predominantly by box diagrams, including top quarks. We will discuss the details tomorrow, how we actually compute this. But what is just important for us now is that the phase in these amplitudes is given by VTB, VTD squared combination. And similarly, the phase difference between the B decay to J psi k short and B bar decay to J psi k short is given by the phase difference of the corresponding tree-level mediated CKM elements. So the CKM elements which enter the tree-level dominated decay amplitudes. And these are just VCB VCS star over VCB star VCS. Times the phase, times the K naught bar phase difference, which again is similar to the B case. In the KM case, this is being dominated by charm box diagrams. So we obtain another factor of VCD star VCS, VCD VCS star. And plugging all these contributions together, we obtain that lambda psi k short is given by this particular combination of CKM element products and ratios, which is nothing else but the minus e to the minus 2i beta angle of the CKM triangle. And then translated this to the observable as psi k short. So this is the prefactor of the sign of the delta MT time dependence of the time dependent CP symmetry in B not decaying to J psi k short is then given by sinus of 2 beta of this angle, okay, which is what we had in our discussion of the constraints on the CKM triangle in the beginning of this lecture. So what we observe here is that since we are actually measuring the phase differences, where the first phase is coming from the relative phases of the B naught and B naught eigenstates, and the second phase is the relative phase of the B naught to K short and B naught bar to K short decay amplitudes, we are actually, in this measurement, we are actually measuring CP violation in interference between oscillation and decay amplitudes. And at present, these kind of measurements allow us to probe experimentally this sin 2 beta angle to an accuracy of approximately 1%. So since I'm running out of time, so here I've worked out in some detail how we derive a constraint coming from CP violation in interference between the mixing and decay amplitudes. In a particular case, I will just briefly go through other measurements which I presented in the CKM triangle plot, which allow us to probe CP violation in other interferences. And I will go through this briefly, but you will have all the slides at your disposal to actually go back and look at this in more carefully at your own rate. So before that, just a brief comment on doing the same kind of measurement of time-dependent CP violation in the B sub S system. There are a couple of caveats when one does that. First of all, the B sub S oscillations are much faster than B sub D oscillations, so the measurement is much more challenging. But also, delta gamma S is not as negligible compared to delta MS as in the B sub D system. So then the formula becomes somewhat more complicated. But nonetheless, these measurements are being performed by LHCb in particular, but also by Atlas and CMS at the LHC. And just for illustration, this is the current status of the measurement of the this phase in between the relative phase between the B sub S to psi phi and B sub S oscillations as performed by LHCb, Atlas, and CMS. And the average, the combined, so these, as I said, because delta gamma S is not negligible, these measurements then depend on delta gamma S, and they need to combine the measurement of delta gamma with the measurement of this phase. And we see that the current state of the art, so this phase is very precisely predicted in the standard model. So the standard model white in white is basically just, you don't see the width actually of the standard model prediction in the phase, while the delta gamma S is much more difficult to predict in the standard model. So there is a big uncertainty in that. But this can actually be determined with considerable precision already now experimentally. And we see that the current experiments have already established that there seemed to be a non-zero phase, not with large significance yet, but it's consistent, definitely consistent with the predictions in the standard model. So we've starting to also establish the presence of superviolation in the B sub S system being consistent with the CKM predictions. Okay, so this is the current state of the art also numerically in terms of the standard model predictions of the phase and then the current experimental measurements. And they're, of course, consistent. Now, as I mentioned very briefly, one can measure different manifestations of superviolation. Another one, which is interesting, is to probe superviolation in B decays to CP conjugate states. So previously, we've talked about decays of B decays to CP eigenstates, but another example is looking at decays of B decays to CP conjugate states. This is interesting when, for example, B naught to F bar or B naught bar to F are forbidden. So some of these decay amplitudes vanish, as is, for example, in semi-leptonic B decays, as an explicit example of this. And then one can define these, in principle, time-dependent decay rates or asymmetries, which turn out to be time-independent. So it's a time-independent measurement. And is a probe directly of Q over P or P over Q deviations from 1. It's a time-independent measurement, and it measures since there is no superviolation, there are no superviolating phases or interferences in the decay amplitudes because they don't interfere. This is a measurement of superviolation purely in mixing. It's also sometimes called indirect superviolation. And one example of this are the so-called semi-leptonic CP asymmetries. In this case, it's written for B naught, but one can write the same asymmetries also for B sub S. Again, they can be predicted fairly precisely in the standard model, and they have been measured by LHCb. They're being measured by LHCb and previously have been measured at the Tevatron. And we see that the recent LHCb measurements are in reasonably good agreement with the standard model predictions, also for these time-independent semi-leptonic CP asymmetries, which measure superviolation in mixing. And finally, a third class of measurements which are sensitive to superviolating phases are actually measuring superviolation in charged B decays. In particular, I will discuss here the decays of B plus minus to D K plus minus. And what is interesting here is that since B decays don't oscillate, this allows to probe superviolation in decays, but also that one can determine these superviolating phases using rate measurements only. There are no CP asymmetries involved. So a very brief discussion of this is the following. So these measurements rely on the fact that, contrary to the previous cases, here the decay amplitudes are not dominated by a single decay amplitude, but they have two decay amplitudes which compete with each other, and they're governed by different weak phases. And this is the case for B decays to neutral, so charge B decays to neutral Ds and charge kaons. So here we can parameterize the decay amplitudes to different CP combinations of initial and final states in terms of two dominant amplitudes, which have a relative weak phase, which turns out in this case to be just the phase gamma, and a strong phase. Now, we observe that by measuring all the four different CP combinations of such decay rates, we can actually determine all the parameters which govern these decays, namely the dominant modulus of the amplitude, the ratio of the moduli of the two amplitudes, the relative strong phase, and also the relative weak phase. And to conclude, this is a current world average of such measurements performed mostly by LHCb of measuring the different charge B decay amplitudes to neutral Ds and charge kaons. And one can then, using these rate measurements, one can extract all the parameters which govern them, and one of them being the CKM angle gamma. And the world average here of all these compendium of measurements is in this plot is denoted with the green, a small area. And from this one can extract, nowadays one can extract the gamma angle, the CKM triangle, to better than 10 degrees or so. So since I'm again over time, let me conclude here with this discussion of the determination of the CKM parameters. And tomorrow we'll shift to discussing first how we actually predict some of these observables in the standard model, and especially the rates, so the charge currents or the flavor conversion rates in the standard model, and also how we can interpret this in terms of then bounds on possible new physics contributions in terms of using effective field theory methods.
Very nice. Thanks a lot. Let's see if there are other questions from the students. Seems not for the moment. Or in any case, if you want to make any questions directly to Yerney, you can write him, or you just ask the question at the beginning of the next lecture.
Sure.
Well, thanks a lot.
I understand that it could take a bit to digest the material today, because as I already said yesterday, it's a bit more technical.
Yeah, more technical, but it was very clear, and it is necessary to see that at least once in a life.
Exactly. That was the point of this, to see how the technical details of how this is actually done in practice. Yes.
So I cannot see any other questions. So let's see tomorrow at 10.
Okay.
Thank you again. Bye, everybody.